Hello again. What we're going to know is we're going to take a look at how we might code some of those checksums. So we've seen quite a few of them and they kind of have a number of features in common, so we don't need to code all of them, but we're going to look at how we might tackle some of those. Checksums aren't nearly as important as you might think from the fact that I've spent a whole week on them. But they are wonderful programming exercises. So they're beloved by computer science lecturers the world over because, there's lots of loops and counting and extracting things, and things have to happen in a certain order. So they're great programming exercises. The first one we're going to look at here is example 22.php. And this is code to validate PPS number. So this is the number that Irish people get when they are born. It is also the number that non-Irish people get when they first interact with the state, if they move to Ireland. What we're only going to look at tonight is the old-fashioned PPS number that is 7 digits followed by a single letter. If you arrived to Ireland in 2013 or later, you would have gotten a longer number that would have 2 letters at the end. We're not going to look at that tonight. Okay. Also, in example 22, what I have done is sort of built up the code quite slowly, and I haven't generated an actual proper function. And then what I do in the next example is I've just converted that then to a function. So this is the code I was kind of using as I was writing it to develop it slowly. One of the things we would like to be doing when we are processing input from the user is we might decide we want to remove any trailing or leading spaces. So what I'm going to do here is I'm going to remove all of the spaces before and after the text. Now, also what I've done here, and this is something I like to do when I'm writing a validation function, is set up a variable at the beginning and assume that the input is good. And then if ever we come across a reason why the input is bad, we'll set that variable to false. But it's important that once this variable is sort of knocked down and set to false, that we don't ever pick it up again. So if we're adopting this approach, we should only set it to true at the beginning, and then after that only ever set it to false, never set it to be true. Now the first thing I'm going to do here is I'm going to strip away the trailing spaces. So there's this trim function in PHP, and this will strip away all of the leading and trailing spaces. So now when we output this the next time around, we'll see the PPS number that we entered, but we'll see that the spaces around it are gone. I've just put these dashes here just so we can see that. So when we run the code, we can actually see that. Now, we looked at some regular expressions for validating input, and this is what we're going to do here. So we're going to use the regular expression to make sure that it looks something like 1, 2, 3, 4, 5, 6, 7, Q. So we want 7 digits and a letter at the end. Okay. You'll recall that when we're specifying the pattern using a regular expression in PHP, we put these slashes on either side of it. But the main body of the regular expression is that, in fact. And this regular expression is looking for a digit 7 times. And then it's looking for a letter between lowercase a and lowercase w, or a letter between uppercase A and uppercase W. If you recall, when we saw the way this checksum works, the letter at the end corresponds to the mod 23 value, and that can be 0 to 22. We do A1, B2, C3, and so on, and the letter at the end of the PPS number can be anything between A and W. So there's no X, no Y, and no Z. So it's tempting here to say A to Z and A to W and A to Z again, and that wouldn't be a big deal, but actually since we know X, Y, and Z are dodgy, we might as well just not include them at all. And then we can straight away know that there's something wrong there. Here I am just echoing out to the screen to say that's not good. This is just while I'm debugging the code, while I'm writing the code, I can see where something has gone, where something has failed. This is just for debugging. When the program is finished, it wouldn't work like that. A function would never have a side effect like that where it would output things to the screen. So this is the expression, the regular expression. This is the thing we want to compare to the regular expression. Here we're using PREG match. So this would be true if it was a match. So by saying not then, in front of that we're saying, well, if it's not a match, say that's no good and change still good to false. Now, if the number is dodgy, realistically speaking, we should now have a big if to say, if it's still good, do this. Because of course, if the number itself is dodgy, any assumptions we make about how it looks and the programming we do to that could easily fail. I mean, if it's an empty string, for example, and we go extracting things out of it, it could cause a big problem. I haven't done that here. I've got straight down to business, really. So this is a particularly interesting checksum calculation and a particularly challenging one to program, because we are counting through the number character by character. So we are going from 0 to 1 to 2 to 3 to 4 to 5 to 6. So we're counting up here. But the first number we multiply by 8, the next number we multiply by 7, this one we multiply by 6, this one we multiply by 5, this one we multiply by 4, this one we multiply by 3, and this one we multiply by 2 by 2. So that's counting down. So one way to do this would be to have a loop that counts up and then manually keep track of the multiplier. So that would start at 8, and then as we go around the loop we'd say, multiplier gets multiplier minus 1, so that the multiplier would go 8, 7, 6, 5, 4, 3, and 2. That's a bit brutal, I suppose. There's a more elegant solution. If we look here at the relationship between the loop counter and the multiplier, we can see that when it's 0 it should be 8, when it's 1 it should be 7, when it's 2 it should be 6, when it's 3 it should be 5, and there's a relationship between them. Whatever I is, the multiplier is 8 minus I. Now, it took a bit of head scratching for me to figure that out. I mean, I had to write it down on a sheet of paper. I knew there was some relationship between them, but it took a bit of thought. And sometimes you have to think, though, if you want to write, elegant code. So, here we are now then. We have a loop that goes from 0 to 6. It doesn't actually get to 7. It stops short of 7. We could equally have said here I less than or equal to 6, and that'd be perfectly fine. I left that at 7 because it just reminded me that there are 7 digits, Should be there actually. Yeah. Just remind me that there are 7 digits, but of course the first digit is 0. When we're looping through, when we're extracting something out of a string, the first item is item number 0. So this string has 7 characters in it, or the bits we're interested in are 7 characters, but the first one is 0 and the last one is 6. No. So we're going to count through the string from excuse me, from 0 to 6. And as we go, we're going to put the ith item into a variable called digit. So variable digit gets substring ppsn I1. So we're going to, starting at the ith character of the string ppsn, extract a string of length 1, which will be just one character. So in this example here, that's not a good one. In this example, this will be character number 0, this is I number 1, I2, I3, and so on. No. So we have, in digit now, we have the ith character of the string ppsn. Up here we started a running total of the values, and we set that to 0, we initialize that to 0 in the beginning. And now in here, each time we go around, we're saying sum gets sum plus digit multiplied by, and here we have this 8 minus I. So instead of having a separate variable that's a multiplier to keep track of what we should be multiplying, is it 8, 7, 6, 5, 4, 3, or 2, we know that whatever I is, the thing we're going to multiply by is 8 minus I. Now I've done something here that I've cautioned against many times, and it's a feature of PHP, not a unique feature, but not unique to PHP, but it's a feature of PHP that you can take a string variable, and if you treat it like a number variable, well, PHP will have a go and it'll be fine. So I put a character into digit, so digit was a string. Here I'm using digit as though it was a number, and I'm getting away with that. There are quite a few programming languages that will not allow you to get away with that. And so in that scenario, you have to perform an additional step where you create another variable that's a number, and there's a function you can use to convert a numeric string to a number. So like the string 53 and the number 53 are not the same thing at all. In many programming languages, they are totally different, and if you treat the string 53 as if it was a number 53, bad things will happen. PHP will give it a lash, but that's not to say you should take a practice like this with you to another programming language. So anyway, back to this line again here, just to recap. So the running total gets sum plus the digit that we pulled out of the string. So let's say we pulled out, the character at position 3, whatever the digit that was. That gets multiplied by 8 minus I. And so this gives us a total then. Now, so in this program here, I've just output the total so you can see it. You can see what that might be. So my expectation is that you will run this with various made up PPS numbers, and of course your own, and then you can see how the program would treat those, and it outputs different things at different times. What's very interesting is the sum that we get. So we now have a number, you know, that could be, you know, whatever, 492 or something. And we're going to do a mod 23 of the total that we got. And they're going to put that into a variable called checksum. So that now in checksum holds a value between 0 and 22. And that value must correspond to the position of the letter in the alphabet in order for the checksum to be correct. So here we are extracting the last character from the PPS number, which would be the letter. So in this case it would be Q. And that is in check letter. I'm outputting this here just so we can have a look at it when we run the program. Now, it's possible that the check letter was entered in lowercase. And from the computer's point of view, a lowercase q and an uppercase q are completely different characters. So here I have just forced the letter to be uppercase. So if it was lowercase, now it's uppercase. If it was uppercase, it's still uppercase. So we can be certain now that the last character, provided it was a letter in the first place, but we know it was because it passed our regular expression test, that now is an uppercase letter. Okay? And I've output that then here just so again we can have a look at what it is. Now the next part of the problem then is quite interesting, and this could wreck your head a little bit. We need to map the letters to numbers. So we need to map the letter that was at the end of the PPS number to its position in the alphabet. Or alternatively, we need to map the checksum that we calculated when we did the mod 23 to ensure that to see what that corresponding letter would be. Either of those approaches would be fine. So what would the matching letter be? So let's say we want to take the checksum value and figure out what letter that should be. Well, like if it's 1, we want the letter to be A. If it's 2, we want the letter to be B. If it's 3, we want the letter to be C. If it's 4, we want to get the letter D. Now how can we go from 1, 2, 3, 4, 5, 6, 7 to A, B, C, D, E, F, G? Well, one way is a very long switch statement with like 20, in this case 22, 23, whatever, prongs to it. And that would be a perfectly fine way to do that. However, there is a little bit of jiggery-pokery, I suppose, or magic even we can do. Internally in the computer, characters are stored using a system known as Ascii, which stands for the American Standard Code for Information Interchange. Actually, I'm going to call that up there. You've probably seen this before. I'm going to call it up there in just a second. Swoosh. There we go. So this is the Ascii table. And this tells us the mapping of characters to the numbers that are used to store them internally in the computer system. So pretty much all computers now use this system, and internally in the computer each character is stored using a number, and there's a standard mapping of characters two numbers. So we can see here that uppercase A is 65. Space, for example, is 32. You'll notice that lowercase a, which is over here, is actually 97, which in fact is 65 plus 32, which, if you know about your bits and your bytes, you could see why that would be. There's only a 1-bit difference between the uppercase and lowercase. And so each character in the computer system is stored using a number. And we can look up that number if we want. So pretty much every programming language will have a way to take A and get 65, or to get 65, and to take 65 and get A from that. You can go from the character to the number, or from the number to the character. Now, so we want to go from 1, 2, 3, 4, 5, 6, 7 to A, B, C, D, E, F, G. Well, here's the trick we could do. If we add 64 to the number, we would end up with the ASCII value of the letter that we want. So we want to go 1, 2, 3, 4, 5, 6, 7. We want to get A, B, C, D, E, F, G. Well, we can go add 64 to the 1, 2, 3, 4, 5, which will give us 65, 66, 67, 68, 69. And those will be the ASCII values of the letters that we want. Then we can take those values and use whatever built-in function there is to convert those to the letter that we want. So here I'm saying the checksum now gets checksum plus 64. So now the checksum should have the ASCII value of the letter that we're interested in. So we can do one of two things now. We can convert the checksum plus the 64 to a letter and see if that is the same as the letter at the end of the PPS number. Alternatively, we could take the letter at the end of the PPS number, get its ASCII value, and see if it's equal to the checksum plus 64. That's what I've done here. So this ORD function takes the string, takes a character here, and evaluates to its ASCII value. So if check letter was A, then ORD check letter would be 65. If check letter was B, then ORD check letter would be 66. So what we're saying here is the checksum that we got and added 64 to the same as the ASCII value of the letter at the end of the PPS number? If it's not, then we're not happy. So if the letter and the mod 23 checksum calculation that we did aren't equivalent, then it didn't work out. And so it fails. So that's pretty much it then. We can see that running, or you can see that running. You can run it and you can see how everything works. You can mess about with the values here and see how the checksum is calculated. You can see what mod you get. You can see then what letter that should correspond to and whether it all works out. There is a catch. It's always a catch. We're mapping the numbers to letters using A gets 1, B gets 2, C gets 3, D gets 4. But of course mod 23 can result in 0. And mod 23 will give you a value between 0 and 22, not a value between 1 and 23. Now, there is no letter at the alphabet in position 0. We start A with 1 and B is 2. There's nothing at 0 under normal circumstances. For our PPS check letter, it turns out that if the mod 23 results in 0, well then the letter is W. So if you see someone with a W at the end of their PPS number, that tells you that when you do the 8, multiply by 8, by 7, by 6, by 4, by 3, by 2, and add them all up and do mod 23, the 23 goes in evenly and gives 0 as a mod. So this will actually only work for 22 out of 23 PPS numbers. 1 in 23 PPS numbers won't work properly here. It will reject them even though it should accept them. So I'm going to leave that as an exercise for you to fix. It just means putting in an exception in the right place and just checking to see if it does actually turn out to be 0 and then figuring out a workaround to make it work. It won't actually require much code, but it will require you to understand the code that is here. But it's just 1 or 2 lines once you figure out what's going on. Next up now, I'm going to look at the same code here, just coded as a proper function. So what you're looking at example 22 is sort of how I figured out how to make it all work. I need to tidy that up now and put it into a function that returns true or false if the number that's passed in is a valid number or not. Okay, so here we have the code and we have declared a function here called good PPSN. And this takes a parameter. The function definition doesn't say what type that is. That doesn't happen in PHP. In other programming languages, you might have to say what kind of type you're expecting to come in. But we know that's going to be a string. In this line here, we are just stripping away the leading and trailing edges. And then once again here, we have the regular expression test where we're comparing this string here against the pattern in the regular expression. And if it's not good, then we're going to do this. Now, this return false here does 2 important jobs actually. The first job it does is it says that the result is false. So this function is going to evaluate to false. Or we'll see later on, it might evaluate to true if everything was good. But in this scenario, because it's not a match for the regular expression, it's false. Now, a function, as well as doing something, becomes something. So you can see here, we treat good PPSN as if it were a Boolean expression. It's something that's going to evaluate to true or false, and it fits into a true or false sized hole, so to speak, in the code. So an if statement, it needs to do its job. It needs something that's true or false, and it does what it does depending on whether that value is true or false. And this value here will be true or false. So this returning here returns true or false, and the function will evaluate then, in this case, to false. Return does another important job. It stops the code from carrying on. So none of this here gets executed. When we do return in a function, we bomb out of the function and everything else that remains is no longer important. It's not executed. And that's actually useful because if you go back to the previous example, the longer example, if the test here failed and we concluded that the PPS number was dodgy, it still actually carried on with the rest of the code and did things. And there were definitely some scenarios in which carrying on would have resulted in the code crashing. I mean, if we try to extract something out of an empty string, for example, we could be in trouble. Or if we try to do something with a letter when it needs to be a number. We were expecting a number, but a letter turned up. So if there was a letter somewhere in here, in the previous example, in example 22, we could have crashed the code. We could have been in trouble. But here now, we don't have that problem because return takes us out of the function and we're done. We're finished. So from this point on then, it's safe to assume that we do have a string that is in the format that we're expecting. So it's safe to assume that we do have 7 digits followed by a letter. If we didn't have 7 digits followed by a letter, well, we wouldn't be here. We'd have left the function already. So the code then is, as we've seen before, we're having a running total. We have our loop. We go around. Like I said, this when you see it, I think makes sense. But you have to trust me when I say there was quite a bit of thinking had to go into that just to figure out what it should be. None of this is new to us. And then here we're applying the same test again. We're taking the checksum, which was the mod 23, plus 64 as it happens, and we're comparing that to the ASCII value of the check letter. And if it isn't a match, then it's false. So we return false. If we haven't left already at this stage, we can return true. Okay. You could reasonably ask why we don't just say else, else return true here. And that would work fine too. And that would be perfectly acceptable. It would perhaps even be preferable. It's arguable. I have to say I'm a bit paranoid when writing functions in that I don't like to put the returning, I don't like the return of the function to be dependent on some condition. In case the condition doesn't work out the way I was expecting, I always feel like that it's better to return an answer, definitely return an answer, even if it's the wrong answer. Than no answer at all. But that's just paranoia. Really, in this scenario, would have made complete sense to put it in the else. It would have been fine. If it's not one thing, it has to be the other. There's no issue there. So then I'm just putting the string here into a variable called number, passing in num, and like I said earlier, this will evaluate to true or false, and that's important. If needs something true or false in here to work properly. And if it's true, the number is good. If it's false, the number is dodgy. So we can see that running. I'll just save that just to be sure. And we do that there. If we put in uppercase or, obviously it's going to work fine too. No, I'm just trying to think if I change this to 7 here. It should give us test that it's not happy because they won't all add up, and sure enough it's saying look dodgy. Just trying to think there, if this was 7, it's tempting to think that this should be RS, but actually remember this gets multiplied by 2, so in fact the check letter should be 2 letters after R if I'm not mistaken, so Q R S T. Save that there. So here we go. Yep, so that's good. Again, lowercase t will be fine too. And if we change one of these numbers here, it'll be not happy. So there we go. So that's kind of working. Happy enough with that. When I say kind of working, of course, as with the previous example, I haven't sorted out the mod 23 equals 0 being equivalent to the letter W. I haven't sorted that out. So you need to figure out how to do that. Again, shouldn't take long. Now, next up we have example 24, and this is going to do the EAN. So the international article number is the 13-digit number that you see on a barcode. It's an example here. And this is a system used pretty much worldwide now for identifying products. It was initially the European article number before it became more widely adopted. We still call it EAN actually, and when we're abbreviating it rather than IAN. And you'll recall from the class on this that we basically multiply every second digit by 3. So we like don't multiply, don't multiply, don't multiply, don't multiply if we're starting at the back. Because it's an odd number, we know that the first digit doesn't get multiplied, it's the second. So 0, 1 gets multiplied, 2 doesn't, 3 doesn't, so on. So every second digit gets multiplied by 3. We add them all up, and if it's evenly divisible by 10, yip-de-doo, we're good to go. So let's take a look at the code for that. So as with the PPS number, we have a function here. We called it good EAN, and we're passing in a parameter, a single parameter. And in time, this will evaluate to either true or false. You might get the impression from our functions that so far that a function necessarily evaluates the true or false. No, it can return any particular type, any type. It'll return only one value, and that'll be of only one type. But a function can return a number as well, but we're returning Booleans here. Now, what I want to do here is I want to strip out any possible dots and dashes and things. So in a number like this, it may happen that people, put in dashes, for example, or maybe even spaces. And there's even the possibility of dots, really, okay? So what I want to do is I want to strip out anything that is a space, a dash, or a dot, okay? And there is a function built into PHP that does just that, okay? strtr, and this is in essence a find and replace function. So it normally takes 3 parameters where you give it the string that the first parameter is the string that you're working on. The second parameter is the thing you want to find, and the third parameter is the thing you want to replace that with. Now, when I used that to replace spaces with empty strings, I ran into difficulty. I don't know if I was doing something wrong or if it just doesn't deal with that particular scenario or what. So I did give up. Sometimes you just give up. And I used the more complicated way of using this function, where you give it 2 parameters. The first parameter is the string that you're working on. And the second parameter is an array of find and replace pairs. So you specify, if you find this, replace it with this. If you find this, replace it with this. If you find this, replace it with this. So this is a bit more cryptic. It's arguable that it's shorter. I'm not even sure it's a whole lot shorter, to be honest. But anyway, so here we have an array, and we have like space and empty string, dash, single dash, empty string, and dot, empty string. So if we pass this array in as a parameter, it has the effect then of 3 separate substitutions where we do space, empty string, dash, empty string, dot, empty string. So it's a bit more complicated way of doing it. And obviously if you have lots of these, you know, it makes sense. The overhead of being more complicated is worthwhile. If you're just substituting one thing, it's probably overkill. Anyway, I had this code in here just when I was writing it for debugging. You would never expect a function like this to actually output stuff, but it was handy while I was figuring out what was going on. So I just commented that out. You can uncomment that if you want to have a look and see what's going on. Now, so we're using then the regular expression technique to check that this fits the pattern that we're interested in. And the pattern that we're interested in is a digit, so something between 0 and 9, 13 times. Now you might say, well, what about the dashes and the things like that might be in there? Yeah, but we already got rid of those. They're all gone now. So there are no dashes, no dots, no spaces. So at this stage, if we're not left with 13 digits, we're not happy. So if we don't have just 13 digits, no more, no less, and only digits, we're calling foul on that. And we say this isn't any good, and we return false. So false comes back to the calling code. And of course, this return means we stop, we don't go any further. So that's important because we can assume now then that we do have 13 digits. Because if we didn't have 13 digits, well, we wouldn't be in this part of the code. We'd have left already. So this is not entirely dissimilar to the PPS one. It's much simpler. I think we started with the most difficult of all of them. So in the EAN, again, we have a running total. This time we're going from 0 to 12. We don't get to 13. Again, I could have said less than or equal to 12 here, but the less than 13 just reminded me that it is the 13-digit number, you know. It's just a hangover from the fact that it's 13 digits. Less than or equal to 12 would be perfectly fine. The important point is that we go from 0 to 12. We never get to 13. This code here is extracting out the ith digit from this string. Excuse me. So the first time around we have whatever, the next time around we have whatever. So it's only a single character and it's a digit. Now, we need to do something different every second time. So when I mod 2 is equal to 1, we're on the odd numbers. So yeah, so it's like every second 1. Yeah. I have to confess, the first time I wrote this, I did it backwards. I was doing every even one. That's the kind of thing that's going to happen. But anyways, this does every second 1. Just have to make sure, you know, if you're going left, right, left, right, left, right, you make sure you start on the right foot. Okay? Now, so if I is odd, we're going to take the digit that we extracted and multiply it by 3 before adding it to the running total. If it's even, we just add it to the running total as is. We don't multiply it by 3. Again, I've done that thing here that PHP allows you to do, which is take a string of digits and treat them as if they were a number. You can do that in PHP and get away with it. So now we have our running total, and if that running total is evenly divisible by 10, yip-de-doo, the number is good. If it's not evenly divisible by 10, well then it's failed. So we return false. If we passed all those tests, then we know we can return true. And as I said in the previous example, We could, of course, just do this also, and that'd be perfectly fine. Because if it's not one thing, it's the other. Here in my test, I have put in dots and dashes and spaces. I mean, there is an argument that someone types in this, they really are just acting the maggot and they deserve to fail. That someone would only use dashes or dots or spaces. They wouldn't mix and match them. But who cares? We let them away with it, right? So we can see this running now. So 24. So it's happy with that. If we change any of the numbers, then it should give out to us. Obviously, if we remove the spaces and things like that, it's going to have no impact on the checksum calculation because all of those will be stripped out anyway before we do any work. If we change any one of these, if I change this to 5, it won't add up. If you think about it, if I've increased this by 1 here, what do I need to do for the checksum to be good? I need to increase this by 1 here. No, 1 or 2? 3. 3. I need to increase this by 3. Is this going to work? Woohoo, I rock. Okay. If I increase this by 1, then the total needs to be 1 more or 1 less. 1 more, I think. Oops, sorry. Yeah, should never do this kind of thinking on the fly. Is it going to work? No, it was never going to work. It should be, if that's going to be 1 more, there should be 1 less. Let's try this. He's making it up. Okay. Anyway, that's a dodgy number. Okay. So you can take any old barcode off any product you have lying around, slap it in there, and see that working. And this is complete. There's nothing left to be done in this particular one. Unless you wanted to strip out more stray characters. If you wanted to strip out anything that wasn't a digit, there isn't really a short way to do that. You just have to loop through character by character and extract the character. And if the character isn't a digit, then you discard it. And if it is a digit, you'd add it to a new string that you're building up, if you really wanted to do that. Okay, so that's the EAN. It's probably the simplest of all of them that we've looked at. You can see it's a cousin of the loan algorithm that we use for credit cards, and it was certainly inspired by that, but it's a lot simpler. There are less shenanigans. Now, next up we have el DNI, or DNI, which is the ID number that Spanish people have. And as I pointed out, their majesties have special numbers. They had the first 100 digits reserved for the royal family, which I guess puts a time limit on their reign. And what happens is this: you have 1, 2, 3, 4, 5, 6, 7, 8 digits followed by a letter. The 8 digits are treated as an integer, and we do a mod 23, and then the value we get for the mod 23 gives us an index into this table here, which tells us what the letter should be. As far as we could establish, this was totally random. It may even once upon a time have been a state secret or something. It is notable that 10 gets you X. So the former king Juan Carlos has 0000010. X is his number. So that's always a handy one to remember if you're stuck for a number. Like I mentioned in class, the number of times you'll be asked for this in Spain is extraordinary, really. Now, let us move on. So, one issue is that Spanish people have a tendency to separate the letter from the rest of the number with a dash. So we need to account for the number with and without the dash. In this particular example, I've decided that we're not stripping out anything weird. It's all in one go. There's no spaces, no dots, nothing allowed, except possibly that dash in that place before that one letter. Okay? So, this is example 25. Let's take a look. So once again, we have a function. This time we call it good DNI, and it's going to come back then with true or false, depending on if it fits the format. I am stripping out all the trailing and leading spaces. I think that's fair enough, but I won't allow spaces inside. And then I'm doing a trick here which can save some time later. I'm forcing everything in the string to be uppercase. So if it was a lowercase t, well, now we know it's an uppercase t if it's there. If there's a letter there, it's uppercase now. Okay? So when it comes then to checking the format of the string using the regular expression, we don't need to account for the possibility of lowercase letters. Look, it's either uppercase letter or something's wrong. Because if it was lowercase, well, yeah, okay, but it's uppercase by the time we get to the regular expression. So we don't have to check for lowercase. There are no lowercase letters left in that. Okay. This was just debugging code I used. I've left that there as a comment. You can uncomment it if you want to see the effect of the trimming and the converting to uppercase. So we're looking for 8 digits. Okay. So 0 to 9, 8 times. And then there's a dash, a single dash, or not. So there may or may not be a single dash, followed by a letter. Okay? So another approach, more consistent with what we've done before, is we could have just stripped out the dash and then know that we are dealing with 8 digits and a letter at the end. Because if there was a dash, well, maybe there was, maybe there wasn't, but either way, it's gone now. But I haven't done that. And also, had we taken that approach, it would allow for multiple dashes all over the place, which I've decided I'm not allowing in this scenario. No, so if it doesn't fit that format, if it's not 8 digits followed by a letter or 8 digits followed by a dash followed by a letter, then we're not happy. We're saying it's not a good number, returning false, and as I mentioned before, that return will stop the function. It won't carry on because it's done. So we can presume now from here on that we have something that looks like what we're expecting it to be. So my next step now is to extract the numeric part of the string. So we're saying variable big num gets substring DNI08. So starting at character number 0, which is the first character, give me a string that's 8 characters long. Okay, it's some programming languages the substring is slightly different, but I'm actually not going to talk about. I was about to talk about those, and I thought, no, why confuse you? Okay, so this is this take from DNI starting with 0, something that's 8 characters long. Now, so this big num here is a string of digits, but actually, like I said before, PHP allows us to treat a string of digits as if it was a number. So we can safely do a mod 23 of that number, and that will give us our checksum. So checksum now is a value between 0 and 22. Remember, a mod 23 won't result in 23 ever. Okay, I have some debugging code here that's still there if you want to uncomment it just to see what the checksum is. And next thing we're going to do then is we're going to pull out the last character. Now actually we don't know if that is character number 8 or character number 9. It would depend on whether we have a dash or not. As it turns out though, one of the weird forms of substring allows you to extract things from the back end of it. So here we're saying give me a substring of DNI, one character long from the end. So starting one character in. I haven't specified how long, so just goes to the end. So this here is saying starting one character from the end, which is the letter. So even if it's a long one or a short one, the letter is the last letter, so we're good to go there. So now check letter has the letter in it. So we have the number from 0 to 22, and we have the letter. What we need now is some way to map either the letter to the number or the number to the letter. When we did the PPS, we had a cool trick. We used maths and Ascii because the letters were like A1, B2, C3, D4, E, and so on. So that was grand. But these letters here are pretty much in a random order. So what we're doing then is we're using this string pause function. And with this, you give it two parameters. Well, when you give it two parameters, you give it this long string that you're searching for something in. So this is the haystack, so to speak. And then you give it the string that you're looking for. So this is the needle. And it will come back with the position of this string. It'll come back with the position of the needle in the haystack. So if I passed in W, for example, it would come back with 0, 1, 2 as an answer. If I gave it X, it would come back with 10 as an answer. So it gives you the position of the needle in the haystack. So the position then of the letter in this string should correspond to the value of the checksum if everything is right. Because we've engineered this string that way. I mean, this is the table. So this is much more convenient, much shorter than a whole bunch of ifs. I mean, you could say if the letter is 1, then if the checksum is 0 and the check letter is T, then it's good. Else, if the checksum is 1 and the letter is R, it's good. Else, if the checksum is 2 and the letter is W, and so on. Okay? So this is a much more elegant way, I think, of doing this. So then we are checking the checksum value, which was the mod 23, against the position of the letter that we extracted from the end of the string in this string here. If they're the same, woohoo, we're good to go. So I haven't done an if here. I haven't said if this is true, then return true, else return false. I'm just saying, well, look, return this. Okay, this turns out to be true or false. That's your answer. Send back that. This will be either true or false. Whatever it is, that's the answer. So send that back. So we can see then this will actually work with all of these. You can try that yourself. I'll pick one there at random. These are just made up numbers, by the way. I don't know enough. Well, actually, I do know enough Spanish people, but I didn't ask them for their numbers. So that's a good one there. If If I change any one of these, it'll stop working. Interestingly, I couldn't hazard a guess as to what we would do to change these. Let's do this one here. Oops. Put that back there now for you guys in a minute. So this one here is good. Now, if this was 2, right, the check letter then would be 1 more. It should be 1 more than what it is. So what comes after C, K? So this should be K. I think that'll be good. Well, actually, I suppose I should show you that it's wrong first. So that's dodgy, but if we change that now to C, K, because K is the next one. Because there's no multiplying here involved, it's a bit easier to figure out, apart from this mysterious secret string. Yep. Okay, so that's cool. I think we will remove the K there as well, just to see that working. Remove the lowercase k, just put that in, just to show you. So it seems to work all of the times it should work, which is good. The next question then is, does it not work when it's supposed to not work? And there is actually a bit of a mystery, which I want you to try and solve. 23i comes back as good. So this number would be some as of yet unborn prince or king, or princess or queen, and it comes back as a good number. It's actually not a good number, okay, because when it's 23, the check letter should be T. So why does I work? That is a very interesting mystery and a good cautionary tale. Okay, so that's the code for 3 checksum calculations, or most of the code for 3 checksum calculations. It turns out that checksums, aren't that important, but they do make for wonderful programming exercises. So what I'd like you to do now is to take a look at the other checksum calculations that we had and see if you can write the code for those. You can use the 3 examples I've given you as a template and maybe mix and match elements from them. One of the more challenging ones, I guess, is the old ISBN 10 number. That's an interesting one. You could also look at the Polish PESEL number. The French one isn't that interesting, just big. But have a look at those and see if you can program them up. They're very good exercises.